Tonight, we drift into a realm where the very fabric of reality unravels, where the certainties we cling to in our waking lives dissolve into a shimmering haze of probabilities. We journey back to a time when the greatest mind of the 20th century, a man whose very name became synonymous with genius, found himself locked in a profound, almost spiritual, struggle with the universe he had so brilliantly illuminated. This is the story of Albert Einstein and his lifelong, often agonizing, dance with the enigmatic world of quantum mechanics, a dance that even today leaves us with the most profound and beautiful of mysteries. For decades, the universe had seemed a grand, predictable clockwork. Newton's laws, like a divine blueprint, dictated every celestial waltz, every falling apple. Then came Einstein with his theories of relativity, revealing a cosmos far more fluid, more interconnected than anyone had dared to imagine. Space and time, once thought immutable, became interwoven threads in a cosmic tapestry, bending and stretching with the presence of mass and energy. It was a revolution, a testament to the power of human reason to unlock the universe's deepest secrets. Yet, even as he reshaped our understanding of the very large, a new, unsettling truth was emerging from the realm of the very small, a truth that would challenge his deepest convictions and ignite a debate that continues to echo through the halls of physics. This was the dawn of quantum mechanics, a theory born from the perplexing behavior of atoms and their constituents. It was a world where particles could be in two places at once, where observation seemed to conjure reality into existence, and where the very act of measurement irrevocably altered the measured. It was a world of inherent uncertainty, of probabilities rather than certainties. And for Albert Einstein, a man who believed in a universe governed by elegant, deterministic laws, this was an affront. He famously declared, "God does not play dice with the universe." But did God, in fact, have a different game in mind? And was Einstein, despite his unparalleled brilliance, destined to be on the losing side of this cosmic wager? Tonight, we seek to understand the heart of this conflict, to explore the arguments, the thought experiments, and the profound philosophical chasm that separated Einstein from the quantum revolution he inadvertently helped to ignite. Join us as we delve into the final mystery, the reluctant revolutionary to truly grasp Einstein's struggle with quantum mechanics. We must first understand his own revolutionary contributions to its birth. It's a paradox, isn't it? The very man who would become its most ardent critic also provided some of its foundational pillars. In 1905, his Annus Mirabilis, Einstein published 4 groundbreaking papers that would forever alter the landscape of physics. Among them was his explanation of the photoelectric effect, a phenomenon where light striking a metal surface ejects electrons. Classical physics, which viewed light purely as a wave, couldn't adequately explain this. Einstein, however, proposed a radical idea. Light, in certain circumstances, behaves not as a continuous wave, but as discrete packets of energy, which he called quanta, later to be known as photons. This audacious concept, building on Max Planck's earlier work on blackbody radiation, earned him the Nobel Prize in Physics in 1921. It was a triumph, a brilliant insight that validated the nascent idea of quant. So, Einstein, the reluctant revolutionary, had inadvertently opened the door to a world he would later find deeply unsettling. He had shown that energy, at its most fundamental level, was not infinitely divisible, but came in discrete chunks. This was the first tremor of the quantum earthquake. Yet, even as he championed the photon, Einstein remained deeply rooted in the classical worldview, a world where physical properties were definite, where cause and effect reigned supreme, and where the universe unfolded according to precise, deterministic laws. He saw the quantum as a tool, a mathematical convenience to explain certain phenomena, but not as a fundamental description of reality itself. He believed there must be a deeper, more complete theory waiting to be discovered, one that would restore the elegant order he so deeply cherished. This was the seed of his discontent. For while his work on the photoelectric effect hinted at the particle-like nature of light, other experiments continued to demonstrate its wave-like properties. This wave-particle duality, where something could be both a wave and a particle simultaneously, was the first major conceptual hurdle. It defied classical intuition, demanding a new way of thinking about reality. And as other brilliant minds, like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, began to construct the full edifice of quantum mechanics, the implications became even more profound, and for Einstein, more troubling. The universe, it seemed, was far stranger than he had ever imagined, and its strangeness was not merely a temporary inconvenience, but a fundamental truth. The stage was set for a clash of titans, a philosophical battle for the soul of physics. The dice-playing god *, the year is 1927, the place, Brussels, Belgium, the 5th Solvay International Conference on Physics. It was a gathering of the greatest scientific minds of the era, a veritable who's who of quantum pioneers. Einstein was there, of course, a revered figure, but also a dissenting voice. Arrayed against him, primarily, was Niels Bohr, the brilliant Danish physicist and the leading proponent of the Copenhagen interpretation of quantum mechanics. This interpretation, which quickly became the dominant view, asserted that quantum mechanics was not merely a provisional theory, but a complete and fundamental description of reality, and its implications were, to Einstein, deeply unsettling. At the heart of their disagreement lay the concept of indeterminism. In the quantum world, the precise position and momentum of a particle cannot be known simultaneously. The act of measuring one property inherently disturbs the other. Furthermore, the outcome of a quantum event, like the decay of a radioactive atom, is inherently probabilistic. We can predict the likelihood of an event, but not its exact occurrence. For Bohr and his colleagues, this was simply how nature behaved at its most fundamental level. For Einstein, it was anathema. He believed in a universe where every effect had a cause, where every outcome was predetermined, even if we lacked the knowledge to predict it. He famously quipped, "God does not play dice with the universe." He was convinced that behind the apparent randomness lay a deeper, deterministic reality, a set of hidden variables that, if discovered, would restore order to the quantum chaos. This was not merely a scientific disagreement. It was a philosophical clash of titans. Einstein, a child of the Enlightenment, sought a universe that was rational, orderly, and comprehensible to the human mind. Bohr, on the other hand, argued that our classical intuitions simply broke down at the quantum scale. He posited that we couldn't truly visualize or comprehend quantum reality in classical terms. The wave function, a mathematical description of a particle's state, wasn't a physical wave in space, but a representation of our knowledge, or rather, our lack of complete knowledge about the particle, and the act of measurement, according to Bohr, caused this wave function to collapse, forcing the particle to choose a definite state. This measurement problem was another point of contention for Einstein. He believed in an objective reality independent of any observer. The idea that reality itself was somehow influenced by our observation was to him deeply disturbing. Over the years, Einstein tirelessly devised thought experiments, ingenious conceptual challenges designed to expose the perceived flaws in quantum mechanics. His goal was to demonstrate that the theory was either incomplete or led to logical contradictions. But time and again, Bohr, with his profound understanding of quantum principles, would deftly counter Einstein's arguments, showing that the thought experiments, when rigorously analyzed within the quantum framework, actually reinforced its predictions. The debates were intense, respectful, and ultimately deeply influential. They forced physicists to confront the most counterintuitive aspects of quantum mechanics and solidified its philosophical foundations. But for Einstein, the dice-playing God remained an unacceptable proposition. He continued his quest for a more complete, more deterministic theory, a quest that would lead him to his most famous challenge to quantum mechanics, the EPR paradox. Spooky action at a distance of all the perplexing phenomena predicted by quantum mechanics, none troubled Einstein more than entanglement. It was the ultimate affront to his cherished principle of locality, the idea that an object can only be influenced by its immediate surroundings. In 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a paper that became known as the EPR paradox. It was a brilliant thought experiment designed to demonstrate that quantum mechanics must be incomplete. Imagine, if you will, two particles born together in a quantum event, forever linked or entangled. According to quantum mechanics, these particles remain in an indeterminate state until one of them is measured. But here's the mind-bending part. If you measure a property of one particle, say, its spin, the other entangled particle, no matter how far away it is, instantaneously assumes the opposite spin. There's no time for a signal to travel between them, not even at the speed of light. It's as if they communicate telepathically across vast cosmic distances. Einstein famously dubbed this phenomenon spooky action at a distance. For Einstein, this was unacceptable. It violated his understanding of causality and locality. How could information travel faster than light? He argued that the particles must have possessed these definite properties from the moment they were created, even if we didn't know them. The quantum mechanical description, he contended, was incomplete because it didn't account for these hidden variables. He believed that a more fundamental theory would reveal these hidden properties, thus eliminating the need for such spooky instantaneous connections. Bohr, however, had a different perspective. He argued that the EPR paradox didn't expose a flaw in quantum mechanics, but rather highlighted the limitations of our classical intuition when applied to the quantum realm. He maintained that the entangled particles were not independent entities with pre-existing properties, but rather a single, indivisible quantum system. The act of measuring one particle didn't transmit information to the other. It simply revealed a property of the interconnected system. The spooky action wasn't about faster-than-light communication, but about the holistic nature of quantum reality. For decades, the EPR paradox remained a thought experiment, a philosophical battleground. But with advancements in experimental physics, it became possible to test entanglement directly. In the 1970s and 80s, experiments by physicists like John Clauser and Alan Aspect provided compelling evidence that entanglement was indeed a real phenomenon, just as quantum mechanics predicted. These experiments, and many more since, have consistently shown that the correlations between entangled particles are stronger than anything classical physics could explain, effectively ruling out Einstein's hidden variables hypothesis, the universe, it turned out, was even stranger than Einstein had imagined. His spooky action at a distance was not a flaw to be corrected, but a fundamental feature of reality. It was a testament to the profound interconnectedness of the quantum world, a world where particles, once linked, remain intimately connected, regardless of the vast distances that separate them. Einstein, despite his profound contributions, found himself on the wrong side of this particular debate. But his challenges, his relentless pursuit of a more complete understanding, ultimately served to strengthen the very theory he sought to undermine. The mystery deepened, not diminished. The enduring legacy of a disagreement Albert Einstein never fully reconciled with quantum mechanics. Until his dying day, he held onto the belief that it was an incomplete theory, a stepping stone to a more profound and deterministic understanding of the universe. He spent his later years in a solitary quest for a unified field theory, a grand theory that would seamlessly merge gravity with electromagnetism and, ideally, incorporate the quantum world into a single, elegant framework. He sought to find the hidden variables, the underlying reality that would banish the probabilistic shadows and restore the classical order he so deeply craved. Yet, despite his personal reservations, Einstein's challenges to quantum mechanics were not in vain. His relentless questioning, his insistence on clarity and completeness, forced the proponents of quantum theory to sharpen their arguments, to delve deeper into its philosophical implications, and to design experiments that would ultimately confirm its most counterintuitive predictions. The Bohr-Einstein debates were a crucible in which the foundations of modern physics were forged. They illuminated the profound conceptual shifts required to understand the quantum realm and highlighted the limitations of our everyday intuition when confronted with the universe at its most fundamental level. Today, quantum mechanics is not just a theory. It is the bedrock of modern technology. From the lasers in our DVD players to the transistors in our smartphones, from the MRI machines that peer inside our bodies to the promise of quantum computing, the principles that so troubled Einstein are now harnessed to power our world. The reality that Einstein found so unsettling has become the engine of our progress. And the spooky action at a distance he so famously derided is now the basis for quantum communication and the tantalizing possibility of a quantum internet. So, what is the final mystery? Is it the inherent weirdness of quantum mechanics? The fact that reality at its deepest level defies our classical understanding? Or is it the profound lesson learned from Einstein's struggle? that sometimes the universe is not obliged to conform to our preconceived notions, no matter how brilliant our minds. Perhaps the final mystery is the ongoing human quest to comprehend a reality that constantly pushes the boundaries of our imagination. Einstein, in his relentless pursuit of a deeper truth, even in his disagreements, served as a beacon, guiding us to confront the most challenging questions about existence. He showed us that true scientific inquiry is not about finding comfortable answers, but about asking ever more profound questions. The universe, in its infinite complexity, continues to whisper its secrets. And in the quiet moments, when the world outside grows still, we can almost hear the echoes of that great debate, the clash of titans, the profound philosophical struggle that shaped our understanding of reality. Einstein, the reluctant revolutionary, the critic, the seeker of hidden variables, ultimately left us with a legacy far richer than he might have imagined. He left us not just with theories, but with a testament to the power of intellectual courage, the beauty of persistent questioning, and the enduring mystery of a universe that, even without playing dice, continues to surprise and awe us. And in that awe, perhaps, lies the true final mystery. Conclusion. The story of Einstein and quantum mechanics is not merely a historical footnote in the annals of physics. It is a timeless narrative about the nature of scientific progress, the limits of human intuition, and the profound humility required when confronting the universe's deepest truths. Einstein, with his unwavering belief in a deterministic and local reality, found himself at odds with a theory that embraced probability and non-locality. His objections, born from a deep philosophical conviction, were not easily dismissed. They forced the quantum pioneers to rigorously defend their ideas, to refine their interpretations, and to ultimately prove, through painstaking experimentation, that the universe, at its most fundamental level, operates in ways that defy our everyday experience. Einstein debates, often portrayed as a clash of personalities, were in fact a profound intellectual dialogue that pushed the boundaries of human understanding. Bohr, with his pragmatic acceptance of quantum weirdness, argued that we must simply describe what we observe, even if it defies our classical sensibilities. Einstein, on the other hand, yearned for a deeper, more complete picture, a reality that existed independently of our observation. His insistence on a hidden reality, while ultimately disproven by experiments on entanglement, nevertheless spurred the development of quantum information theory and the exploration of the very foundations of quantum mechanics. The tension between these two giants, between determinism and probability, locality and non-locality, completeness and inherent uncertainty, continues to resonate today. While quantum mechanics has proven to be an incredibly successful theory, providing accurate predictions for a vast array of phenomena, its interpretation remains a subject of ongoing debate. Is there a deeper reality beneath the quantum veil, as Einstein hoped, or is the universe fundamentally probabilistic, as Bohr contended? These are not merely academic questions. They touch upon the very nature of existence, our place within the cosmos, and the limits of human knowledge. The legacy of Einstein's challenge is not that he was right about quantum mechanics being incomplete in the way he envisioned. Rather, his legacy lies in the profound questions he posed. questions that continue to drive research and inspire new generations of physicists. His skepticism forced the scientific community to scrutinize quantum mechanics with unprecedented rigor, leading to a deeper and more robust understanding of its principles. Without Einstein's persistent challenges, the philosophical underpinnings of quantum mechanics might not have been so thoroughly explored, and its counterintuitive implications might not have been so firmly established. And so, the final mystery endures. It is the mystery of a universe that refuses to conform to our expectations, a universe that is both elegantly simple and bewilderingly complex. It is the mystery of a reality that, at its most fundamental level, operates on principles that defy our everyday experience. Einstein, in his magnificent struggle, showed us that even the greatest minds can grapple with the universe's profound strangeness. He taught us that the pursuit of knowledge is not always a straight path, but a winding journey filled with unexpected turns, profound insights, and enduring enigmas. As we close our eyes tonight, let us ponder the universe that Einstein and Bohr debated, the universe that continues to unfold its secrets, one quantum leap at a time. Let us embrace the mystery, for in its depths lies the endless wonder of discovery. Good night, and may your dreams be filled with the strange and beautiful dance of the cosmos.